So for this week's material on linear programming, I want to do a little bit of a quick review here first on graphing inequalities, and specifically two variable inequalities. So if we're looking at graphing linear inequalities, we have four possibilities. We have the strict inequalities, which is just your less than or greater than. And then we have non-strict inequalities, which is less than or equal to, greater than or equal to. And remember, that includes, when it has the or equal to on it, that means it includes that boundary condition. So we're looking here at the four possibilities again, looking at how we can solve these inequalities the same way we do an equation, adding, subtracting, multiplying, or dividing to both sides. The biggest thing you have to remember is if you multiply or divide by a negative, you do have to flip the inequality symbol, as we see down here. There we go. So we have several types of inequalities. We're going to look at, if we start out with just a single variable or more, two variables unknown, it's the same way we can manipulate them. If it's just a single unknown, we solve it like a linear equation, and we can get a boundary value, and we would graph it on a number line. So you'd end up with something, for example, possibly x less than or equal to 4. We find 4 on the number line, and x is either equal to it or smaller than it. That solid dot means that that boundary line, in this case the 4, is included. If it were, if I change my ink color here, let's say it were x strictly less than 4, well then it would be an open dot like that. So saying that the 4 is not included, that 4 is not a solution. So for linear inequalities, like we said, single variable, double variable, or even 3 or 4 variables, we have coefficients on each of those variables, and those coefficients define the shape. Now for us, for a single variable, it's easy. We can graph it on the number line like we did in the last example. 2 variables, x and y typically, we can graph it on our coordinate plane. It's when we get into 3 and 4 variables that we really can't graph it anymore. So we have to look strictly at algebraic methods. So some quick examples. The first one up here, 2x plus 8 is greater than or equal to 89. That's a linear inequality in a single variable, so we could do that on a number line. You would solve that subtracting 8. So 2x is greater than 81, and then you divide by 2 to get x is greater than 40.5. So on your number line, greater than or equal to, that should be. On the number line, you'd have 40.5. It'd be a solid dot or a square bracket, depending on which version you're using. And the arrow would point to the right because it's greater than. For the second one down there, 2x to the third is less than or equal to x to the third plus y. First thing we notice is it has 2 variables, x and y. So it's 2 variables. Second, the power on the x, that x to the third, means this is not linear. So this is not going to be a linear inequality. It doesn't mean, well, it's only 2 variables, x and y, so we most likely can still graph it on our standard Cartesian plane, but it's not going to have a line as that boundary condition. So similarly, a solution in an inequality in x and y is a pair of values that makes the inequality true. So what the whole purpose of this, any graphing, is to find the solution to the equation. When we graph a line, any point on that line, if we take its x-coordinate and its y-coordinate and put it into that equation, it'll make the equation true. Well, since this is an inequality, it's not just the points on the line, it's the points on one side of the line or another. The line that we draw, if it's a linear inequality, actually divides the graph into 2 regions. One region is the solutions, the other region are the points that are not solutions. So let's solve a linear inequality with 2 variables. Let's start out with this example here. 2x plus 3y is less than or equal to 6. First thing we do is we turn it into an equation. This is going to give us that boundary on our graph. just going to treat it as 2x plus 3y equals 6. To graph that, we could either solve it into y equals form, or we can just use the intercepts. 2x plus 3y equals 6. We take that constant 6 divided by the 2, the coefficient of x, we get 3. 3 is the x-intercept. Take that constant 6 divided by the coefficient of y, which is 3, we get 2. 2 is the y-intercept. And our line goes through those points. Now, for the linear programming we're going to do, these are going to pretty much always be less than or equal to, greater than or equal to. So it's going to be a solid line. But recall, if it was strictly less than, we'd have to make a dotted line because the points on the line technically don't make the inequality true. Here, though, because it's less than or equal to, the points that are on the line are equal to 6. So that is still true since it's less than or equal to. But now, like I said, that line divides the graph into two sections. One section that contains solutions, another section that is not solutions. To figure that out, we typically use a test point. If it's obviously on one side of the line or another, I like to use 0, 0. And if you plug that in, you'll see if it's true or not. So here, like I said, there's points on one side of the line, point Q. If point Q makes that true, well then that's the side that has the solutions on it. So like I said, we pick that test point. I usually use 0, 0. Now we're going to do something that will appear backwards at first, but it's simpler to sketch the sets of solutions rather than inequalities. So let me show you what I mean here. So typically what we're used to doing, we try that test point 0, we put 0 and 0 in there. 2 times 0 plus 3 times 0, is that less than or equal to 6? Remember, that's our inequality was less than or equal to 6. Well, 0 is less than or equal to 6, so that's true. That means this side of the inequality contains the solutions to that inequality, or this side of the line, I should say. And we're used to, typically in our algebra classes, we shade in the side of the line that contains the solutions. Here we're going to do it backwards. We're going to black out the other side, that's the side that's not the solutions. The reason for that is in linear programming, the side that satisfies the equation is the side we want to keep. This is the side we're interested in using. So we're going to keep it, unshaded so that we can work with it. So we black out the side that is not the solution. So to sketch the region represented by linear inequality, first you make the straight line that's implied by the inequality of the equation. Choose a test point. Usually 0, 0 is good if it's obviously on one side of the line or the other. And then if the test point satisfies the inequality, that's the side that's the solution. If the test point does not satisfy the inequality, the other side is the solution. And of course, we're not shading in the solution, we're blacking out the side that's not the solution so that we don't use it anymore, to show that we can't use it anymore. So here are the three steps. We've got the inequality, x plus 2y is greater than or equal to 5. Well, 5 divided by 1 is 5, so the x-intercept is 5. 5 divided by 2 is 2.5, so the y-intercept is 2.5. Our line goes through there. It's greater than or equal to, so it's a solid line. Like I said, in this chapter, all of our constraints are going to be greater than or equal to or less than or equal to, so it's always going to be solid lines for us. We sketch that line. We pick the test point 0, 0. We put 0 into this inequality. 0 plus 2 times 0, is that greater than or equal to 5? Well, that 0 is not greater than or equal to 5, so that's not true. So the solutions are over here, which means we're going to black out that side. So for each of these examples, sketch the regions and sketch the regions that are defined by each of those inequalities. So A, 3x plus or 3x minus 2y is less than or equal to 6. So 6 divided by 3 is a positive 2. 6 divided by negative 2 is a negative 3. There's my intercepts. Line goes through those points. I test 0, 0. 3 times 0 minus 2 times 0. Is that less than or equal to, less than? Yeah. Equal to 6? Well, yes, it is. 0 is less than or equal to 6. So this is where the solutions are, so we black out that option. For the next example, 6x is less than or equal to 12 plus 4y. We can rewrite this into standard form. I can subtract the 4y from both sides to get 6x minus 4y is less than or equal to 12. 12 divided by 6 is 2, so 2 is our x-intercept. 12 divided by negative 4 is negative 3, so negative 3 is our y-intercept. They're dividing by 2 to simplify the inequality. We really don't have to. We're going to get the same line either way. So we can see that they simplified it to this form. Usually it's the same as this form, just been divided by 2. Again, I would be perfectly comfortable graphing it in that form rather than dividing it out by 2. So let's go through it. Like we said, we've got positive 2, 6, 12 divided by 6 is positive 2. Negative 3, so our line goes through those points. 0, 0, I put that in there. I go back to the original when I test my points just to be safe. Well, 6 times 0 is 0. Is that less than 12 plus 4 times 0? Yeah, 12 plus 4 times 0 is just 12, and 0 is less than 12. So that's true. So we're going to black out this other side over here. The region x is less than or equal to negative 1. Well, x is equal to negative 1 is just a vertical line at negative 1. Less than or equal to would be over here. If I try 0, 0, 0 is not less than or equal to negative 1, so that's not the solution. So our solutions are over here, so that's why we black out this other side. The region y is greater than or equal to 0. Again, y equals 0 is just the x-axis. So we can't choose the 0, 0 as our test point. We have to find a different point here. So we pick 0, 1. So we put 0 in for x. Well, x isn't even in the inequality. Put 1 in for y. 1 is greater than or equal to 0. So that's true, so we black out the other side of that line. Finally, the line x is greater than or equal to 3y. The boundary line would be x equals 3y. We're not used to graphing in that form, so we're going to divide by 3 here to get 1/3 x equals y, or y equals 1/3 x, which means we have 0 for y-intercept, so it goes through the origin, the center of our graph, goes through 0, 0, and has that slope of 1/3. So again, because it goes through the origin, we can't use 0, 0 as our test point, so we use 0, 1. 0 for x, 1 for y is 0, greater than or equal to 3 times 1. 0 is not greater than or equal to 3, so that's not a solution. The solutions are on the other side of the line over here, so we black out that side. So sets that are completely enclosed by boundaries are called bounded. And that's what for the simplest form of linear programming, we want bounded sets. Areas that are not completely enclosed, so they can extend infinitely in one direction or another, or many, are called unbounded. And to do those in linear programming, we'll see in the next section that we have to artificially impose bounds upon that. And we'll see those examples in the next section. So that's it for the review of inequalities. We'll start talking about linear programming in the next section.